All right, today we begin Unit 1, and Day 1 is all about function characteristics. We have two critical questions for today. And number 1 is, what characteristics would you need to know in order to graph a function? Number 2, what connections can be made in order to make predictions about problem situations? We are going to explore a specific problem and talk about each of the questions individually. And here is the problem. As a promotion for the Texas Rangers ballpark, a competition is held to see who can throw the baseball the highest from the front row in the seats, which is approximately 10 feet off the field level. The winner throws the ball with an initial vertical velocity of 92 feet per second, and it lands on the infield grass. The height of the baseball as it relates to time can be modeled by the equation h of t equals negative 16t squared plus 92t plus 10, where h of t is the height in feet of the baseball at any time t in seconds. Question number 1. Sketch a graph illustrating the height of the baseball as it relates to time. Number 2. What would be a feasible domain for this and range for this problem? Number 3. On what time interval is the height of the baseball increasing? Number 4. On what time interval is the height of the baseball decreasing? Number 5. What is the maximal height that the baseball reaches? Don't forget your units. Number 6. At what time is the maximum height reached? Number 7. When will the object reach the ground? And number 8. How much time was the ball in the air? Okay, let's start first with number 1. We are going to sketch a graph illustrating the height of the baseball as it relates to time. So the first thing you're going to want to do is enter the function into your calculator. And so I have a TI-83 here, and I placed the h of t function, which again is down below here, as negative 16x squared plus 92t plus 10. So you'll notice up in the calculator that I've put in x's everywhere t is, because it doesn't matter which variable that you use. Let's proceed. So when I push graph, or in my case, I think it was zoom 6, I get this graph. And at first glance, it certainly doesn't really make any sense in the scheme of what's happening. We're supposed to see something that might look like throwing a ball and it reaching the ground. And it certainly doesn't look like that's what's happening here. So what we're going to do is fix our window a bit, because right now, if you push the window button, again, if you'll look right here, if you'll push the window button, you'll notice that we are on a very standard screen, and that's probably not awfully helpful for this problem. So I thought, well, I'm just interested in probably that first quadrant right up here. Right here, because someone's going to be throwing the ball and they're going to be having it reach the ground. I'm not caring about here, that's underneath the ground. I'm not caring about over here at all, because this is when we would have negative x values or negative time. So I started my window with an x-min of 0 and an x-max of 10, because it certainly looks like that will be fine. This is 0 to 10 right here. And I scaled it by 1. If you don't know what that means that for every one of these little marks represents x equals 1. And I decided, again, to get this first quadrant that I'm going to go y equals 0, and I had no idea how high up I needed to go. So I thought I'd try 100, and I scaled that by 1 as well. So then I get something much closer to what I'm looking for. However, I still don't quite see that maximum. So I would think in my mind, what part of my window needs to be changed? And x-min and x-max are good. Y-min is good. It's our y-max that's the issue. So I'm going to make it a little larger. Again, I don't know exactly what that will be, but I thought 150 for our y-max. If you'll notice, I put that in. That's the only thing I changed there. And that gives me a good representation of what's going on with the ball as it relates to time. Now let's talk about a couple things before we move on. As we sketch this graph, you would have your window from 0 to 10 here, and these are time values. So you would label it as time in seconds. And this one would be from 0 until 150, and then that would be in feet. So we make sure we label those things when we're sketching. All right, number 1 has been answered. Let's proceed. Number 2 asks for what a feasible domain and range for this problem is. And that would mean what makes sense to this situation. And that kind of goes back to what I was talking about over here. The second and third quadrants of this graph do not make sense to this problem for the reasons I said. Negative time values, negative y values, or negative heights don't make sense. So we need to make, again, a feasible domain and range. And we're going to make a guess here because we don't know exactly how high that ball is going. So a nice feasible domain and range, again, written in interval notation, would be for a domain, I would write a D representing the domain, and I would say that we are going between 0. Again, the first time we start is 0, and I guess there's some argument to be had whether you include it, which just means this includes 0, I'm going to, or whether you wouldn't, because the moment time starts, it's already past 0. I'm not going to pick at you for that. And then we would go as far as, let's count up here. It looks like it's about 1, 2, 3, 4, 5, 6 maybe. So again, we are estimating, so I'm going to say about 6. It's just an estimate, okay? And our range, in the same manner, looks like it definitely isn't going lower than 0. Some of you might be already to say how high that value is right there. I'd take 0 there until about 150 if you wanted to estimate it. Or some of you might already realize that our function up here has a y-intercept, or an initial height, of 10. So we know that it doesn't reach below 10 in the beginning. However, and this is the key here too, it does actually reach below 10 over here. So some of you might be thinking that you could have written 10 to 150, but I would say no, because in fact the range has some values below 10. So your better option again would be the first option we had, from about 0 to 150. All right. Number 3 and 4 that go hand in hand. On what time interval is the height of the ball increasing? And on what time interval is the height of the ball decreasing? So I put back up the screen, the window, excuse me, and the graph that I thought were helpful. And let's talk about the increasing and decreasing places. So again, we're going to estimate. Within this lesson, we'll do some estimating and some not estimating, finding more exact places. So I would definitely say that on this graph that we are increasing from here until we reach that maximum height. So we're going to estimate that. That maximum height is reached at about 3. And for right now, I'm good with that for this part of the question. Lost my cursor again. All right, so we are going to put, I would say that this is increasing from 0 until about 3. Now, I often do not include these endpoints of the increasing and decreasing. In calculus, we don't when we are talking about intervals of increasing, decreasing. But I wouldn't pick at you either if you included them. Let's talk about the decreasing then. Should be about, again, this is approximate on this question. we are going from about 3 until about 6. Again, this is that interval notation, because we travel along, and again, these intervals, which is tough for some kids, is always going to be in terms of that domain value. We are increasing from 0 till 3. We are decreasing from 3 until about 6. All right. Number 5, what is the maximum height that the baseball reaches? And we're going to have to include units in that. And at what time is that maximum height reached? All right. So again, I put up the same graph and window. And you'll need to push second trace, and you come up with this calculate menu. Second trace brings you up here. And we are interested in the maximum. That maximum height is that maximum on the graph. So I'm going to push maximum, which is number 4. And then it produces this screen on the graph. This is left bound. And you're going to want to scoot that cursor by moving your left-hand button, you're going to move it up along here until it comes over here. You want to be on the left-hand side of the top there. And once you get there, which you can see I have right here, you're going to push enter, and it's going to say right bound. And so you're going to do the same kind of thing. You're going to move it from where it was over to the right-hand side of the maximum here. And that's your right bound. And you're going to enter. And then I'm not moving anywhere on the guess. I'm going to enter through that guess and make sure that you get to this screen that tells you that you have reached the maximum here, and it gives you 2 values. Some kids forget or don't reach that point. They have a left-bound screen or a right-bound screen or a guess screen. So make sure that you reach the maximum command. That's what you're looking for. All right, let's write our answer, because it says, what is the maximum height that the baseball reaches? Well, the maximum height that the baseball reaches is going to be that y value of our maximum. So I would say that that is, again, the y value is 142.25. So I would say that the maximum height that we reach is 142.25, and again, your units, feet. Okay, the height's measured in feet. Then our number 6 says, at what time was that reached? So this was our height, and this is our time when that was reached. And I would say at time 2.875. 3 decimal places is always a safe bet if I don't tell you any better. And the units on that would be seconds. Now at this point I want to talk about feasibility of something, that you look at the answers and know that your units make sense. If someone's throwing a ball 142 feet high, makes okay sense. That's pretty high. But for instance, I've seen kids put 2.875 minutes. Now think about if you're throwing a baseball in the air or a basketball towards the basket or anything of that fashion, it is not going to take minutes to come back to the ground. Just a little side note. All right. Number 7, when will the object reach the ground? And 8, how much time was the ball in the air? Okay, this time I need a little bit of different command, because if I'm wanting to know when that object has reached the ground, I am looking for when the height is 0, or when it's crossing this x-axis on my graph. So I think one of the easier ways to do that, and again, we could have estimated at this point, but I wanted to show you some commands on the calculator. We could find a pretty close approximation for it by putting in y2 equals 0, and then finding out where that line intersects that. So let's go forward. So I use the second trace command again, but this time I find out where they intersect, because what's about to happen is you're about to have this y equals 0 line, and you have this quadratic function going on here, and we're looking for where they intersect, and that will be when it hits the ground, right there. All right, so I'm using the intersect command under second trace, and it gives you a first curve, command. And so I'm just going to kind of move that cursor wherever it is to be closer to where I'm looking. I'm looking for where it's intersecting the x-axis there. And then it gives you second curve. So after you've pushed enter there, you're close. So you can just push enter again, and you'll enter through the guess. So then make sure, again, just like last time when we were doing the maximum command, that you get to this intersection. And so I get an x value of 5.857, and I get a y value of 0. We're going to talk about that in a moment, too. Sometimes that's not so pretty. So if I were to write my answer, when will the object reach the ground? I would say at time 5.857 seconds. And if you want to write seconds out, that's okay. If you'd like to just put the S, that's fine too. And how much time was the ball in the air? Again, that's just using what you already know. We know time started at 0 and it ended here. So I would then say 5.857 seconds it was in the air. Okay, for a moment, let's talk about this. Because sometimes our calculators don't come up with as pretty of a value as that 0 is. You might have a 5e to the negative 12th. You might have a negative 6e to the negative 10th. Let's talk about what those mean. So remember back in scientific notation, 5e to the negative 12 means 5 times 10 to the negative 12th power. And negative 6e to the negative 10th means negative 6 times 10, 10 to the negative 10th. So what this means is that I have a decimal point that is here that moves 12 places to the left. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 5. I think you get the point that it's a very, very small number close to 0. Same thing here. Negative 0.1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? Again, it's a negative value, but still very, very close to 0. So keep that in mind when you're using these calculators. Moving on. All right, so that's it for today. And tomorrow we will do some more practice on this, and you'll have the opportunity to do some on your own.